Okay, thanks. Welcome back to the second half of the lecture. So I'd like to move to slide number 27 now. So I've skipped a few slides, as I mentioned, which you can read at your leisure. So we're moving to slide 27, the capacity upgrade paths. And the reason why I think this is an important one is it ties in very nicely to the previous question that we had before the break. And capacity upgrades becomes quite important as we've discussed, because most operators launch with the sufficient amount of coverage, but not the right amount of capacity. And most operators get away with that because there's not many subscribers on the new 3G network, so it's not a big problem. But as the number of subscribers grows, as the traffic per subscriber grows, so the overall traffic grows significantly, then you need to really take into account the actual overall capacity of the network. Some of the upgrade paths are shown here in this slide. So most operators will launch with what's called a one carrier network. So what we mean by that is that they will use only one block of the 5 megahertz that they may have in spectrum. So they're running in one frequency block. And it's shown here as one power amplifier, but what that means is one power amplifier covering all three sectors, which was another question we had during the break. So that's the most simplest form of a base station, where you have one power amplifier across all the sectors. But most operators are actually launching with a three-sector type base station configuration. So the scenario of a 3 power amplifier, one carrier is your typical starting configuration for most networks. So what do we mean by that is that each base station will have 3 sectors, and each sector is individually powered by a separate power amplifier. Okay, but all of those sectors are operating within the one frequency band or block, if you want to call it that. So if you want to upgrade the capacity of the network, you can do, well, there's really only one real path, which is to add more power amplifiers. And the reason you add more power amplifiers is to move into the second carrier. So by adding a second carrier, we end up with a new code tree, which gives us then more capacity for downlink data and uplink data as well. So if you think of each carrier frequency as a separate code tree, adding more carriers will give you more code trees, therefore more capacity. So in order to power the second carrier, you need to have another set of 3 power amplifiers. So that is the ultimate scenario, which is the block on the far right, where we have 6 power amplifiers and 2 carriers. But some innovative techniques will allow you to run 2 carriers with the same 3 power amplifiers as well. So it's a more cost-effective approach to getting to the 6 power amplifiers and 2 carriers. And the reason why you have these intermediate steps is because, some cells, some sites, for example, might be perfectly happy running 2 carriers with 3 power amplifiers, and will never grow more than that. For example, they might be in lower lying areas, low density areas. Whereas some sites, for example, will almost certainly need to have a second carrier already from day one. Actually, I remember one of the network launches earlier here in Australia, there was surprisingly a couple of sites in the CBD, and most of them were in Chinatown, which was interesting, where the first carrier got almost full from day one. So the operator at the time was wondering what was going on there. So I don't know whether there was a lot of free calling. I don't think there was any free calling at that time, so it was quite strange. But there was obviously a lot of people in that small area that were being served by that one cell. And that particular operator didn't have very good sites at the time because they were newly launched, so you can guess who that was. So what they had to do was come up with very innovative techniques in order to distribute the traffic or offload the traffic from that congested site. So some of that would mean changing the configurations and orientations of the base stations around that particular site that had a problem to take on that traffic, and also perhaps using new types of antennas and different types of configurations to actually make that work. So you can see that all of this type of work, which is the upgrading of the power amplifiers, going to second carriers, reconfiguration and retuning of base stations, this is the general work of the RF engineer, essentially, or the operations group within the operator. And it's an ongoing process. It's not something that's done once. It's a continual process that requires real feedback and data from the network. So if you look at, maybe we can skip a couple of slides now, and we'll go down to the slide number 34. Actually, no, why don't we go to slide 33, and that gives you some solutions here which are quite interesting. So slide 33, which looks at coverage and capacity improvements. So the wideband CDMA coverage is generally limited in the downlink because of the low transmit power from the terminal. The problem is more the actual terminal power, because keep in mind the power of the terminal is usually around 0.2, 0.3 watts, something like that. It's quite low. So there's an intrinsic limit to how far the terminal can be away from the base station and still maintain the EBNO that's required in order to support the speech service or the packet service. But we can actually alleviate that problem in some ways by, as we mentioned, adding more sites, using higher antennas, or antennas at higher heights, or antennas with higher gains. There's other techniques that can improve the sensitivity of the base station, which is using two receivers together in parallel, which is called receive diversity. And what that does is it's effectively like having two ears listening to the same signal. Both those signals get added together, and therefore you get a better signal to noise ratio, and then therefore you're able to hear the low level signals. Another one that was always talked about was smart antennas. Now, smart antenna solutions, you can almost think of the smart antenna as tracking the mobile user. In most antennas, you have a fixed lobe configuration, which is the actual area of coverage or the propagation of the actual antenna that it provides. Smart antennas, then, the lobes actually move, if you like, or track the actual subscriber. So the lobes change, the lobe configuration actually changes. So quite complicated, but actually... the question was, does it change automatically or manually? It changes automatically. So based on the measurements that are being taken from the network, the base station is then able to power and control the antenna to actually, to some degree, it's not specifically like tracking a single user, but the lobes change to deliver the power to certain parts of the sector.
So 1 or 2 degrees, like that.
Yeah, something like that. So you can think of in a 3-sector base station, that sector then is broken down into subsectors. And then you deliver power to maybe 1 or 2 of them more so than the third or the fourth one. It's not used. No, it's a good question. Is that actually used? It's very rarely used. It's quite complicated and very expensive to deploy. It was used a lot in some GSM markets, surprisingly. No one, I believe, in Australia is using it. It's, again, too expensive. Another one that's probably more current is MIMO, multiple input, multiple output, which is something you might be familiar with from wireless LAN and WiMAX and LTE. They all use MIMO or will be using MIMO. The complication with MIMO, though, is that you have to upgrade all of your base stations to have 2 antennas. So you can imagine the complexity to go to every single base station and make that happen. And secondly, the terminal needs to also have 2 antennas as well. So that means a mobile operator can't really ring you up and say, hey, I've got this really good plan for you, but you need to upgrade your phone and I'm going to subsidize you. It's a very expensive business. So anything to do with antennas tends to be quite difficult to actually achieve. So operators tend to try and keep that as simple as possible. Do it once and do it right is usually a good approach, but it doesn't always work that way. So the capacity limit is of a network is generally more crucial, and some of the typical types of solutions that we looked at or already discussed are adding more frequencies. Adding more cells is another approach, which is called sectorization, which is breaking up the 3 sectors into 6 sectors. So what that means is that you're able to only deliver power to one of those subsectors, which then saves you more power for other sectors. It's a more efficient use of pooling, effectively, if you want to call it that. Some other techniques are called adaptive bitrate codecs. So for example, the voice codec in 3G is called AMR, or adaptive multirate. So the AMR codec in 3G actually has 8 modes that it runs at. It starts at 4.75 kilobits per second and goes up to 12.2 kilobits per second. So most network operators are running at 12.2, so it's quite good speech quality. However, it typically tends to run at 4.75 in congested networks. So what you can do is, by changing the codec rate, you can actually drop the bit rate and therefore reduce the requirements on the base station for sufficient power to run a service, and therefore squeeze more users in. So that's kind of the approach. Okay, so moving on to the next section. So we're sort of starting to wrap up a little. So we've got the capacity and coverage and planning and optimization section. But in the early part of the lecture, I've actually weaved in a lot of the discussion that's in this section. So if there's any specific questions you'd like to ask me around the capacity and coverage planning part, we can take that now. But I think we've generally covered that already in these next couple of slides. Is there anything any further questions? Okay. So the only part about slide 35 that I'd like to mention to you then is, just to finish off on this whole RNP process, is it is very iterative. It relies on definitely real data, such as your geography, your terrain, and so on. It's based on estimation from your modeling and propagation tools to give you a model of a certain scenario. So that scenario is not going to fit the entire network. It'll fit maybe 3 or 4 of the majority cases that you will find. So pedestrian traffic, CBD, rural, suburban. Those are the 3 or 4 that tend to come up more often than not. And that tends to cover 60 or 80% of the actual subscriber base. So it tends to work out quite fine. But then at the end of the day, the use of the planning tool and the smarts becomes very, very important. And this is where we'll start to discuss in a little bit more detail in the next couple of slides how that actually looks. If you remember back to some of the early lectures around the CDMA, one of the most important aspects of the planning is not actually, well, apart from the number of sites, where the sites are located, the capacity and coverage, the most important fifth part, if you want to call it that, is actually to minimize interference. Interference was the tricky part of a CDMA network. So the more interference we have in the network, what that means is then the power that's used, the power that's available in the network can be less utilized for the capacity and the coverage. So interference is, you can consider it as a negative factor within the network. So how do we actually get interference? Interference is generally driven by too many base stations cluttered too close to each other, for example. You could also consider that as the soft handover area between 2 base stations is too large. So what we're having is a lot of terminals who are constantly in soft handover, drawing lots of power from the network. So we know soft handover is important in order to have mobility in the CDMA system, but we can't have soft handover areas that are too large as well. So there's that balance that we need to maintain as well. One area of interference is also what's called pilot pollution. So pilot pollution is when a mobile phone is trying to connect to a cell, for example, it can actually pick up 6 or 7 other sectors around in the neighboring area. So if for some reason it picks up a sector of a site that is very far away, the near-far effect problem starts to kick in, which is the power in the terminal power goes up and starts to then flood the base stations in the nearby area. And that then adds to the interference of those particular cells for other users. So one of the problems here that we tend to find in mobile networks is what's called neighbor cell planning or neighbor relations. So neighbor relations are very important in helping the mobile phone understand which cell it can jump to when it's moving from one place to the next, as well as what cell it can actually lock on. So let me explain the neighbor cell sort of concept. Every sector will have a list of other sectors that a mobile phone can jump to. So in an area where you've got 3 or 4 sites, for example, you would only want to keep those neighbor cell relations, as they're called, to a very limited subset. So what happens is the mobile phone actually reads the neighbor cell list and says, these are the 5 sectors I can actually connect to, and then does measurements to see whether the signal strength is strong enough in each of these sectors. And if it is, then it will actually make a radio link connection, and it will end up becoming in soft handover. And you might have 2 or 3 radio links connected at the same time. So what you want to try and plan is to make sure that you maintain these neighbor cell relations in a very coherent way, so that you maintain mobility for the actual subscriber who's moving through the network. But at the same time, making sure that you have enough neighbor cell relations, or making sure that you don't limit the neighbor cell relations to too few that the terminal can't actually jump onto another cell. So there's that balancing act again that we're looking at.
If the person living there, in between the two sectors,
Yeah.
and is getting continuously, say, suppose the power of the 2 cells, and it's jumping, once it's jumping, it's getting high power from here, and within 3 seconds, it is getting high power from here, from one room to another room. Then what's going to happen? There's a lot of loss of signal again.
Yeah, the question is what happens if there's a subscriber that is somewhat between 2 base stations, and is there a situation where the signal strength for the duration of the call remains strong enough between the 2 sectors that it's sort of bouncing between the 2 sites? That effect is called a ping-ponging effect, and the ping-ponging effect happens in all mobile networks, actually, GSM as well as wideband, CDMA. So what tends to happen is you want to try and avoid those situations. And if a lot of subscribers are feeling or undergoing a ping-ponging type effect in that region, then you know something's quite wrong with the planning. What tends to happen, though, is you tend to have timeouts as well, where a radio link, where the subscriber is connected to a radio link, will actually get kicked off to stop that sort of thing from happening. But it's very rare that you see that happening these days, actually. Usually the measurement reporting will indicate that there is a lot of ping-ponging effects. So, like, for example, it depends how you set up your network, but there might be a limit to the number of times you can connect to the same cell per second, for example. And those sorts of measures can actually be used to stop that person from ping-ponging. It's very rare to see it happen, though.
Sometimes it's also when the subscribers increase near the BDSs.
Yeah.
BDS size or not be something there's a pocket created.
Yeah.
When subscribers increase and when the BDSs, the network coverage area goes down, shrink.
Yeah.
There's a pocket created. Generally, what should we do?
Okay, so the second question here is in new networks where in new 3G networks, what is quite typical is that you have very spotty coverage. For the reasons that we talked about, you're trying to minimize the number of base stations that you roll out, and what you'll typically find is that you'll get a lot of little black spots around regions between sectors, or between two sites, actually. So as the traffic is increased on the network because of increasing number of subscribers, as well as increasing traffic, what's happening here is that the cell starts to shrink. So that black spot starts to grow and becomes more of a problem. This tends to be a big burden for almost all operators, unfortunately. And the problem that some of the solutions that some of the operators use is very rarely, first one is to add a new site, which is hard to do because you can't always find the right site and it can be quite expensive. The second most used option then is to actually change the tilt and pan of the antennas, is to reconfigure the orientation of the actual antenna. Usually what happens is that because there's not enough traffic on the network, the tilt and pan of the antennas is probably not optimal anyway. So once the traffic is actually running on the network, then you need to keep modifying those. So that's usually what tends to happen. So tilt and pan is simply the orientation and angle of the antenna. So if you can think about moving the angle of the antenna backwards, so to speak, then the radio signal sort of goes up in the air a little bit more, and then hence covers the black spot a little bit better. But at the same time, what it does is it puts a down tilt on the other side where it's actually increased, right? So you've got a problem there. So you need to do 5 or 6 different sites at the same time just to work out one black spot. You can't isolate that one particular problem. That's what usually tends to happen. So moving on to then slide 37. Thanks. These are all very, very good questions. So stop me wherever you like and ask whatever question you have. So moving on to the network optimization, I'll go over this again. It's all about an iterative process. So once you've launched the network and you've done your initial optimization, then the real work actually starts, which is to take real feedback from the network, plug that into your tools and systems, send it off to your marketing departments as well on a very high level so they can understand what's actually going on in the network. And then what you simply do is keep doing this over and over again. So you start off with performance measurements. In order to take certain performance measurements, you need various KPIs or key performance indicators. So some of the classic ones are voice call drop rates, connectivity successes, or connection establishment ratios, for example, packet data throughputs, those sorts of things. Radio link failures, how many times have I failed to connect to a particular site? That is a very good one to actually pick up that there's something wrong on a sector, for example, that I'm seeing a lot of failures. Percentage of users on soft handover, those sorts of things. If you find that your soft handover ratio is anything higher than 30 or 40%, then you know your network is not being planned properly. It should be around that range, just as a rough rule of thumb. Call admission is another one. Congestion on your RACH, which is your uplink channel when you connect to your cell for the first time. There's a number of different KPIs. So taking all of those into account and then mapping it per sector across the entire network on a monthly basis, weekly basis even, is very important in actually getting a good feel for what your network is doing. And then what you simply do is put that through more planning tools and processing tools, and then you tend to get results on what's happening. Keep in mind as well, network optimization is important for the general growth and health and well-being of the network, if you want to call it that, which is to improve capacity and coverage. But it's also used, it's also very important when it comes around to customer complaints. So what you might find is that a certain number of customers in a certain area are experiencing significant problems. It might be because someone planted a new tree one day in front of a base station. Those sorts of things happen. Or a tree has fallen down and hit the antenna and it's now pointing in some other different direction. You don't know these things. So you've got an entire building or apartment users of subscribers who can't make calls, for example. So it's also important in finding faults in the network and then rectifying that as well. Somewhat extreme scenarios, but just to highlight the example of where it becomes quite useful. So some of these networks performance measurements that I talked about is shown here in slide 38. So the mobile makes measurements on a regular basis. When a mobile connects to a cell for the very first time, it connects to or reads what's called the system information block, and that gives it a whole bunch of information. One of those pieces of information is the types of measurements that it should take on a regular basis, the frequency, the interval, and how often it should also report back to the network the result of those measurements. Some of those measurements, for example, are looking for GSM neighbors. Like when I move out of 3G coverage, you need to jump onto a GSM cell, for example. So that becomes quite important. Another one is also more commonly jumping onto a sector in order for soft handover to be achieved. Some of the other ones here, for example, are C-pitch strength, which is to measure the strength of the carrier signal, and blur, which is the block error rate. And that's a very important one. When the block error rate goes down significantly, then you know your radio quality is dropping significantly. When the block error rate drops below a certain level for a particular service, like 64 kilobits per second, the network will actually drop the connection in that case. So the blur is then sent back to the mobile network. There's some other examples here. I've discussed already the neighbor list optimization, which is the downlink measurements. So you can use here is shown a scanner, which is another tool which helps us identify whether our neighbor cell relations are actually built in an optimal way or not. So there's a number of different measurements, and they all need to be aggregated into what's called an OSS, which is an operation support system. So the OSS is really your network operation and maintenance tools and processes as well. So there's a lot of data and a lot of volume of information that's being processed and being stored and analyzed. And as the years go by, I can only imagine that it gets more and more complicated. So what I might do is I might move on to the next and the last, or the second to last section, which is the GSM wideband CDMA planning part. And all I'll simply do is take you to slide number 43. So in slide 43 here, what we're showing is two networks that are coexisting, a 2G and a 3G network. On the left-hand side, you can see the different states of those networks, which is detached, idle, and connected mode. So for 3G, you'll remember from the RRC lecture, RRC has 4 connection states of cell DCH and cell FATCH, cell PCH states, just to name the 3 of them, 3 main ones. Cell DCH is when you have a DCH physical connection, and that is in the normal situation when you're in the middle of a call, for example. So in this particular example here, we have split it also by circuit switched and packet switched. So we have, for example, a circuit switch call on 3G. So that means the user is in cell DCH state, but it's starting to move out of 3G coverage as it moves towards the right. And ideally, it should, of course, want to jump onto a connected mode circuit switch state for 2G. So what the terminal is doing is, it's in the background, it's actually always scanning for GSM neighbors or GSM cells. So the point at which handover will happen is when the network will actually make the decision based on the measurement reports from the terminal. The terminal will say, I'm currently on a 3G sector, the signal strength is really low, the blare is pretty high, but I've got this strong 2G neighbor, which is really good. And it won't say anything. It'll send the information to the network, and the network would naturally make the decision that you're starting to move out of 3G coverage. I'm going to cut the 3G connection and move you, or hand you over to 2G. And the call will continue from 3G to 2G without you experiencing anything. In a badly performing network, you can actually hear clicks and funny pops in the speech call as it makes these jumps. But that's essentially the type of interaction that happens between the terminal and the network then when handover occurs. In the same way, in the next slide, in slide 44, we talked about adding more carriers to add more capacity in the network. So in this particular example, this handover scenario, when we look at intra-frequency handover, that means we're handing over within the same frequency. So for example, we're in frequency 1, which is our initial carrier frequency that we launched the network with. The interfrequency would happen when we move from frequency 1 to frequency 2, which is the second carrier that we added due to capacity reasons. So you can see here that a user in cell 1 and frequency 1 is, for example, moving in the right direction, might actually jump to cell 5 on frequency 2 because the cell 2 in frequency 1 is actually full. So the network can actually jump you to a second carrier as well, depending on the situation and load and configuration of the network. So what we can actually do is we can use 2 carriers to actually manage the capacity of the network and bounce the mobile between the 2 carriers if need be. Generally speaking, that doesn't happen all that often. What tends to happen is that we force a certain number of terminals into one frequency and another set of terminals into another, and somewhat split the subscriber base up that way. Another way to cut it is that HSDPA might only be offered on the carrier frequency 2, for example, which covers the same area as frequency 1, where frequency 1 only offers voice plus basic packet data services. So we can split up our network in that dimension as well. So there's a lot of flexibility for a network operator in order to manage their actual network capacity and coverage. So in the case where we have UMTS coverage, where it is smaller than GSM, which is quite typical in most of the operators today, although it's starting to change, in the early days where UMTS or wideband CDMA was used as a hotspot, the actual handover to GSM became extremely important because that had the full coverage. Consumers would then be able to continue with their voice calls. That was very, very important to achieve. So in that sort of scenario, what would happen is the user would be in their UMTS cell, and as we described, was scanning GSM neighbors in the background, and the network, due to load reasons, would force the user out of UMTS and push them down into GSM. And vice versa as well. If there's too much usage in GSM, can we jump to a UMTS carrier? Yes, let's move our subscribers to UMTS as soon as possible. Now, most operators who have 3G and 2G would like to have their 3G subscriber on 3G all the time. And the main reason there is that it tends to be more efficient to run voice. And secondly, the users actually has access to more services like packet data, portals, and so on. So if the users are sitting on 3G, they're more likely to use these services and therefore spend more money. So it becomes, again, economic reasons for driving this. So we try to keep the users on 3G as much as possible. Okay, then just wrapping up in the next 5 minutes or so. So the last section here on radio network planning tools is just simply to give you an idea of what these tools actually look like. So I've gone through and taken a few snapshots from some various tools that I've seen around the place. So some of the inputs then, just to recap, for these radio design planning tools are the map data, so the terrain, the clutter information, the geography, the layout of the city, for example. We have then the antenna patterns, which is shown on the right. This is the antenna pattern I described somewhat half-heartedly, I guess. But the lobes that I talked about, the actual antenna pattern looks like this red scatter that you see. Although it might be drawn as a hexagon in a very simple chart, it doesn't ever looks like that. So you can imagine that when you're trying to build a radio network and you have sites with coverage patterns that are actually the shape of red rather than a real circle, it's quite easy to see that you'll get black spots and holes and those sorts of things. And these lobe patterns change as well depending on the configuration, the antenna types, and so on. Hence the black magic kind of approach to radio frequency planning. The site data becomes quite important, which is the configuration of the base station, the antenna types, the antenna gain, the tilt and pan of the antenna, those sorts of things. The propagation model, how does the radio signal attenuate in this particular environment? Now take humidity versus a dry desert environment, it actually changes the characteristics of the radio waves as well. Those are also taken into account. Subscriber data, the growth in the number of new subscribers, the traffic profile of the subscribers, both voice usage, minutes of use, calling time per minute, per hour, and also download rates per month, for example. And then finally, the wideband CDMA parameters such as the EBNO, the SEER target, all of those things that we sort of touched upon as well. So you'll see here in the pictures on slide 47, you see the little black spots. Those are actually the base stations. And you'll see in the next slide a little bit more clearly 3 little triangles around a circle. So that circle, or the red circle, is the base station site itself, the location of it. And the 3 triangles actually represent the 3 sectors. And you can see the direction in which the sectors are pointing based on their orientation in the map. And you can start to see also that for the plot on the right-hand side, which shows you packet data at 128 kilobits downlink, 64 uplink, that polygon that has been defined has pretty good coverage. It's all red, although there's some black spots which are in gray. So those are the black spots that we talked about. And those black spots might be perfectly fine. There might be forest areas and jungle where people don't live, for example. Or it might be a creek or a stream and you don't want to cover it, so it's not a big problem. But if it's in a residential area, then you have a serious issue. And then, of course, you need to attend to it by making some changes. Just another look at a planning tool as well. This is actually showing Perth, actually. So it's got Western Australia there, if you recognize the layout. You can see the Swan River. So what all this is showing is just the signal strength of the particular coverage area. And as you can see, near the base station we have very strong signal strength, and naturally as you move further out it's quite a lot lower. And then finally, you can see here, the intention of this slide is to show you how complex it can be, how data intensive it is. As I mentioned, you're collecting all this information from all of these different nodes. They have to be processed and managed at the same time. So for example, as I mentioned, when it comes around to customer care and fault finding, you want to try and correlate the information from the subscribers coming from the call center, which is the irate customer saying I've lost coverage, and then some of the data that you have here to try and diagnose where the problem might be. It could be as simple as a board in the RNC failing, and in which case, 10 or 20 base stations have suddenly gone offline that you may or may not have known about if an alarm came or not. So those are the sorts of day-to-day activities that are the operations part of the engineering group of an operator will actually be involved with. So quite a lot of very data intensive, that's for sure. And one piece that I didn't mention before is that radio network planning is actually all based on coverage polygons. So we tend to break up a coverage area in terms of polygons, and within those polygons, typically one radio frequency or RF engineer will actually be responsible for that area, and he or she will ensure that the site tilts and pans are correct, the configurations are working, that any black spots are attended to, and so on. That's typically how you break up the network design and planning. So the planning tools can actually work in parallel with a number of different RF engineers, each one adding their clusters, as we call them, or polygons together, and then ultimately you'll get an entire radio network map that would be produced. And just a couple of other interesting pictures just to show you more of the same. You can see here in slide 53 the actual signal strengths, and it's all color-coded. It shows you that very similar to the slide that I showed you in regards to the 384, the 128, and the 64, which is on slide number 12. Here in slide 53, you can see the blue, the light blue, the green, and the yellow, which is showing effectively, if you like, a typical type of service area. And then finally, moving on to slide 55, this is downtown Hong Kong. You can only imagine that radio network planning in an area like this must be an absolute nightmare. But somehow it still works, and I think 9 million people are quite happy with their mobile service over there. So mobile networks are, yes, complex, largely because they are based on radio waves and the black magic of radio frequency planning. It is a process, really, at the end of the day, that has to be followed fairly rigorously. More importantly, you start with some pretty fluffy inputs. You hopefully have a good process and a good way of working. You take your outputs and measurements from real world, you put that together and you run it through the machine again, and hopefully in time you'll actually get a very robust and well-performing network. And that usually translates into very happy subscribers. So hopefully the lecture's been interesting and covers a little bit of an industry view of where things are at. And if you have any questions, I'll be around for a couple of minutes if you want. Okay, thanks.